Our guest for today is someone who you probably recognize. She is the star of our Skylog segment on previous shows, Dr. Carolyn Sumners. But of course today she's going to be talking about chemistry, and that's why she's wearing her special tie-dyed lab coat. We're standing, as you can see, in front of the periodic table of elements. Carolyn, why is this table so important?
This is the way we organize the universe. Everything from the clothes we wear to the stars we look at night are made from 92 naturally occurring elements. In our periodic table, you can peer inside and actually see the different elements and what they're made of and what they look like. For instance, this is aluminum. There's an aluminum can. The AL stands for aluminum. The SI is silicon. You make computer chips, solar cells. Inside there is phosphorus. That's what we use to light matches and make fireworks. And if we keep going over, we can even find sulfur, which is a yellow solid. And finally, we come to a gas called chlorine, and we make cleanser out of that.
And we can see from looking inside these little boxes that there are elements that we can touch and some that we can't, like gases. But you've brought some that we actually can with you.
Yeah, this one we already saw. This is sulfur. You can see what it looks like. There's a big bar of aluminum. That's zinc. This is copper. Now you see copper in copper wire, so you're comfortable with that. Lead is heavy. This is carbon in its naturally state.
And that is graphite, right? Which is what we find inside our pencil leads. How is it that the carbon atoms work in the pencil?
Okay. In a pencil, the carbon's arranged in a hexagon like this. This is each a carbon atom. Now, if you put them over here, notice, if you could imagine them being right along this hexagon, they make a nice sheet of carbon. We have two sheets here, and the sheets can slide past each other. When that happens, the carbon comes off on your hand, like you can see here on the piece of graphite I'm holding.
Right.
Also, it comes off of the pencil lead onto your paper, and you can write with it.
Can carbon be arranged in any other way besides in this hexagon form?
Much more beautiful ways. With heat and pressure, you can get one of these. This is a diamond or a tetrahedron. When you make carbon look like that, you can see what it looks like here. Imagine each of these vertices has the carbons arranged in this way. Won't you take it?
And as you can see, this is a lot stronger bonding than what we saw with the hexagons.
You know what it looks like?
A beautiful
diamond ring.
It's hard to believe that that's actually made from the same element that makes the pencil lead.
Graphite with heat and pressure turns into a gorgeous diamond ring.
Much harder and much more expensive. Is there a third way that carbon can be arranged?
We've just discovered that. It's called the buckyball. And in this case, we have 60 carbons. They're arranged in pentagons and hexagons, and this is very stable. You can actually have a gas, a molecule, or an atom of something else inside the buckyball. Here at our chemistry hall, we give you a big version of this that you can look at kind of eye level, and there you go.
There it is.
And the red things are the carbon atoms. You can see them bound together to make the buckyball. This is designer chemistry. We're actually making molecules now and atoms. Here we have silicon, and the silicon solar cell is collecting light and turning it into electricity to make that disk spin. If we cover the silicon solar cell, notice the disk stops spinning.
So, of course, you mentioned earlier that we have 92 elements on the table, but we have a lot more than 92 things in the entire universe. How is it that those are made?
These 92 elements can turn into, by combinations, over 10 million compounds. And 90% of those compounds are made of carbon, mixed with hydrogen and oxygen. You want to make a compound?
Sure.
Okay. The compound we're going to make is salt. Now, to make it, we have to, ordinary salt, we have to have sodium and chlorine. And when we combine sodium and chlorine, it can make quite a splash. First of all, that has chlorine gas in it, the beaker does. We put a piece of sodium in it, and we're covering it up. First, we notice that nothing happens because there's a film over the sodium, so the sodium and the chlorine can't get together.
Right.
Let's drop a little water in.
There we go.
And there it goes. And when you add sodium and chlorine and you mix them, you get a lot of energy released. And when you look down at the bottom of the jar, when everything is said and done,
the smoke is cleared.
You'll find yourself with some table salt, NaCl, sodium chloride. If you want this to really go, you heat up the different elements that you're going to use. We're now heating the sodium in a copper little cup there, and we're going to put it inside the beaker.
Once again, there's chlorine gas in it.
Chlorine gas in the beaker, you're right. Now, at first they don't mix, so we need to shake up the sodium, kind of drip it down so the fresh sodium reaches the chlorine, and then better watch out because
there it goes.
It takes off. So when you mix things, you often get a lot of energy released.
Do all chemical reactions produce energy like this one?
Most of them do, and the ones that we really care about do, because we can store the energy in the chemicals, mix them, and get the energy out. For instance, here we've done that. We have liquid hydrogen, liquid oxygen in the big tank behind the shuttle. When we mix the two of them together, they produce enough energy to take an astronaut into space. At the beginning of the show, we saw that we used electricity to break water into hydrogen and oxygen. Now we're putting the hydrogen and oxygen back together to get the energy back, and what comes out the back of the shuttle is water.
So that's what the trail is?
That's right, it's just water.
Now I understand you have one more demonstration to show for us live. Tell us about the compounds you're going to be working with here.
Okay, this is simple. It's something you can do at home. First of all, we need vinegar, and we'll put vinegar in this bottle right here. So there's vinegar in the bottle. Then we have baking soda. Now I have put the baking soda inside the balloon. They're not mixing right now. Before we mix them, we better take some precautions.
Put on our safety
We don't know what's going to happen here. We've already seen some pretty violent chemistry this morning. All right, are you ready?
I'm ready.
Okay, we're going to lift up the balloon, and there goes the baking soda. The baking soda was a solid, the vinegar's a liquid, and what do we get?
A gas.
That's right, and the gas fills the balloon. That's carbon dioxide, and it's a pretty nifty chemical change you can make from just stuff you can get.
Yeah, a fun experiment that you can do at home.